Hi everybody, my name is Christy. I'm your SI instructor for Dr. Sood's 1145 Chem class, Gen Chem. I'm going to be making several videos to help you through this course. The first video I'm going to make will be ionic compounds, covalent compounds, how to use the periodic table, such and such like that. So I'm going to tilt the camera down. What I like to do with this when we first start is I like to show you how to use the periodic table to think about metals and nonmetals. Alright, so on this side of the periodic table you have your metals, you have your transition metals, you have your staircase of your metalloids, and you have your nonmetals and your halogens. These are your lanthanides and actinides, but you don't need to deal with that right now. I'm going to draw this on the whiteboard and show you guys how you should probably practice drawing it as well. I have found that drawing things, drawing diagrams, drawing a periodic table, it really helps your brain commit it to memory, and that's what it's really all about, right? So when we get past the periodic table, I will go over some worksheets. We'll start with ionic compounds, then we'll go to a worksheet that has mixed ionic and covalent, and then this wonderful worksheet that Dr. Sood has provided us with. Alright, so that'll be the game plan, and let's get started. Alright, so the first thing I like to do is draw myself a blank periodic table, right? Column 1A, column 2A, the middle portion, which are the B columns, with the transition metals. Then we have column 6A, column 3A, column 4A, column 5A, column 6A, column 7A, and let me scoot this down, right? Column 8A. So I've got 1A, 2A, B, 3A, 4A, 5A, 6A, 7A, 8A, right? Alright, and one thing I do like to use when studying is a website, and I'm going to pull it up on my other monitor here, called ptable.com. It's just a really nice interactive periodic table, right? And so on the blank periodic table, I'll start by drawing in my metalloids. This just really helps you, the student, commit these to your memory. And it helps you get used to looking at the periodic table and viewing it as a whole. So I've got boron, silicon, germanium, arsenic, SB, something I cannot remember, maybe antimony, I think, Te, and Po. Alright, so those are your metalloids, and I like to fill that in just so I can designate exactly where the staircase is. Alright, so the next thing I'm going to do, I'm going to switch up the colors. I'm going to use blue for positive, right? Because what happens is you have metals that turn into positive cations, and then you have nonmetals that turn into negative anions. Alright, I'm also going to fill it in just a little bit more. These are your noble gases, right? And the great thing, or the important thing about noble gases is that they are inert, they're stable. And in a couple other videos you should refer to the Bohr model, Lewis dot structures, and even the electron configuration models, and that will give you a better understanding of why we call noble gases noble. It's because they're inert, it's because they're stable, they're happy, they have an octet. Words like that is how we distinguish noble gases. Then you have your halogens in column 7A, and your chalcogens, just kind of wrote that weird, in column 6A. This is carbon, nitrogen, and potassium here. Oxygen, sulfur, and selenium are there. And then all of your halogens are here. So this are your nonmetals, right? And then over here you have your alkali metals. The next one is your alkaline earth metals. And over here, all of these are your transition metals. These are quirky. We'll talk about why we call them quirky in a moment. Over here, everything besides boron is also a metal. Alright, so let's go back down here. We refer to this, right, this section over here that I've marked in blue. We call it kind of like the left side of the periodic table. Quotation marks, left side. And we call this over here our right side of the periodic table. That's kind of how we refer to it. So what happens is our metals, when they are ions, meaning they have lost or gained an electron, they turn into positive ions. And those are cations. They're on the left side of the periodic table. And they lose their electrons. I denote electrons as an E with a superscript minus sign. Okay? Over here on the right side of the periodic table, we have things that gain an electron. So they are negative ions, which we call anions. Okay? They are on the right side of the periodic table. And they gain electrons. Right? So this is your basics of how to, when talking about ionic and covalent compounds, how to really look at the periodic table. So I didn't draw everything in. That's not really necessary. What is necessary is to understand where the things like metals and nonmetals are located. Right? So I have designated them in blue and red as metals and nonmetals. And so the gist of this is that an ionic compound is made of metals and nonmetals that are ionically bonded. So next we'll get into that, what types of bonds you have. Connor, we will totally have to edit this. So in class, you have learned about two main types of bonds, right? You've learned about ionic bonds and you've learned about covalent bonds. So before I give you a simple definition of what these two things are, I think we should talk about what bonds are. And in order to talk about what bonds are, we should talk about chemical reactions, because we're in chemistry, and chemistry is all about reactions, right? So a chemical reaction, you can define it a couple of different ways. I just abbreviated reaction as RXN, reaction. One way you can define it is consuming or releasing heat. You'll get to this definition at the end of the semester. The definition that you should really focus on right now is the definition that is concerned with electrons, because right now you're learning all about electrons, and really electrons is why chemistry happens. It's why you see light, it's why you see colors, it's why things bond. So in that context, a chemical reaction is when bonds are formed, and consuming goes with formed, or broken, and that's releasing. And also heat is a form of thermal energy, so I can put a slash and put energy. Okay? So this is the main point, when bonds are formed or broken. Then that begs the question, what is a bond? In the most simplest terms I can put it, a bond is two electrons. Most simplest definition. So now that we've discussed a chemical reaction and we've discussed bonds, and I just like to keep everything real simple, so I'm not going to go into too much depth with that. But now that we've discussed these two terms, I can go back up here and explain what an ionic bond and a covalent bond is. So an ionic bond is when electrons are stolen, right? So it's when a metal loses electrons to a nonmetal. Okay, so another way of saying that is metal. When a metal bonds with a nonmetal. Okay? In the instance of a covalent bond, electrons are shared. So, and this only happens on the what we call the right side of the periodic table. A covalent bond only occurs between a nonmetal and a nonmetal. So it's on the right side of the periodic table. Ionic bonds occur between things on the left side of the periodic table and things on the right side of the periodic table. You see the difference? Alright, so the next thing we have to discuss is what we call polyatomic ions. And I suppose before we get into polyatomic ions, it might be good to discuss ions. So on the periodic table, you have elements, right? Those elements in atom forms, we usually think of elements. So on the periodic table, you have elements, and in the real world, we have atoms of those elements, right? So the elements that we're looking at on the periodic table, when we look at them, usually they are not charged. They have a neutral charge of 0, right? When you see something like this, or this, right? You notice there are charges on them, right? And we call those ions. So ions are just charged atoms of a particular atom. You can have positive charges or negative charges. Left side, right side. Metal, non-metal. Cations are the positively charged ions, and anions are the negatively charged. Alright, so now that we've discussed that, we can go to polyatomic ions. Poly means many, right? So there are certain polyatomic ions you have to memorize. There's no real shortcut to it. You just have to commit it to memory. The best thing I found to do was to make flashcards. So on one side of the flashcard, take bicarbonate, for instance. On one side of the flashcard, you would write exactly this, HCO3-. And on the other side, you would write the name, bicarbonate. Okay? That's really the best way to go about it. The molecular formula with the charge, and then the name on the other side of the flashcard. And just keep running through them until you know them off the top of your head. And try them both ways. Like, look at the name and see if you can say the molecular formula. And then when you go back through the flashcards again, look at the molecular formula and see if you can remember the name. And just keep doing it until you've got it completely. Alright, so the big thing is with polyatomic ions, most of the ones you have to know are anions, negatively charged polyatomic ions. There's only really one polyatomic cation you have to know, and that would be NH4+, which is ammonium. One, I guess, trick that I really used to memorize the names of NH3 and NH4+. The way I really differentiated between that is this has one less hydrogen than this, and I think it's like the same amount of letters, but ammonia just looks shorter, so I memorized that's a shorter looking word, and there's less hydrogen. And then ammonium, I suppose it's because it has more syllables, just seems longer, and there's more hydrogens there. The thing you need to realize here is that ammonia has a neutral charge, which is why there's no charge listed here. It has a charge of 0. It's neutral. So it is not an ion. It's just a compound. A covalent compound at that. However, this right here, ammonium, it does have a charge, and it's a polyatomic ion, right? Many atoms, ion. Many atoms, ion. So that's a polyatomic ion. And another thing to notice about the polyatomic ions are the thing I just said about this being a covalent compound. Things like ClO2-, SO4-2-. These are like covalently bonded, I guess you could say. It's a nonmetal and nonmetal. But we think of these as together. They're polyatomic ions, so they're kind of together, and as a whole, they have a charge of 2-. You can read your textbook. I know my textbook definitely had an explanation as to why it collectively had these charges, so if you want to learn about that, I know for sure that's in your textbook. So I'm just going to make a run through and show you the ones that you definitely have to know. I would double check your slides that Dr. Sud has posted, because I know she has a more comprehensive list, and I know her list is what you definitely have to know. So, the only polyatomic cation you have to know is NH4+, which is ammonium. It has the atom symbols N for nitrogen, and there are 4 H's. That 4 is a subscript. That plus is a superscript. So there's a difference between sub and superscripts. Sub denotes how many atoms you have, and superscripts denote the charge of an ion. so it has a +1 charge. Another thing you don't really have to know, I guess, but it's important to know, especially when you get into the concept of acids, is that this is H3O+. We call that hydronium, which in this instant it is a polyatomic cation, but we often just shorten it and refer to it as a hydrogen proton. In another video I'll try to explain that. Otherwise you can look on Google, you can look on YouTube, you can look in your textbook and learn more about that, but that has to do with acids. So 2 polyatomic cations are right there, ammonium and hydronium. So let's get into all of the wonderful polyatomic anions. I'll start with, most of them are in the 1- column. So I'm going to shorten it, polyatomic P dot AT dot anions 1-. So we've got HCO3-, which is bicarbonate. You can also call it hot hydrogen carbonate. I just call it bicarbonate. You've got HSO4-, which we call hydrogen sulfate. We've got HSO3-, which we call hydrogen sulfite. So notice how this is SO4 and SO3. It both has sulfur, it both has oxygen, and then the H, which is the hydrogen part. The one that has the more oxygens has the 8 suffix, and the one who has the less oxygen has the I. I've heard some students memorize that this is 8 because it ate another oxygen, so it's got more oxygens, it's a bigger number. That's one way to do that. I know that you don't have to memorize these two, but I want you to hold on to that thought. I'm going to come back to it when we get to the 2- section. Alright, more that you do have to know these, and another one you have to know is the nitrogen containing oxyanions, NO3-, NO2-. So with me telling you that this was hydrogen sulfate and this was hydrogen sulfite, maybe you can predict what this will be. There's no hydrogen here, there's nitrogen, and there's oxygen. So this is a nitrogen containing oxyanion. And we call that nitrate and nitrite. Notice there's one more oxygen here than here. This is 8 and this is I. Alright, so another one you have to know is that this is OH-, that is called hydroxide. In another video I'll talk about something known as functional groups, which you guys have not gotten to, but there's a difference between OH- and -OH, where this is not hydroxide. This is just a dash where other things would be connected or bonded to it, and we call that hydroxyl. So I just want to point out that OH- and -OH are different, okay? This is a different thing called functional groups. This is polyatomic anions. So just wanted to point out that there's a difference there. Continuing on with the anions, you also have this thing called CH3COO-. I was taught to call COO- and COOH Cu. So if that helps you remember it, it's Cu, but it's CH3Cu. And when it has that minus sign, it's called acetate. Going back to the functional group idea, there are certain functional groups in here that give it this name. If it was written as CH3COOH, we would call that acetic acid. Now in class, you guys learned about the polyatomic anions, the covalent ionic stuff, and you at the same time you discussed acids. So one thing I want to discuss here with the acetate and the acetic acid is that when you have something ending in 8, when you add a hydrogen to it, you create an acid, and the name changes from 8 to ic. Okay, that's important. When you have something ending in ite, it turns from ite to us, O-U-S. Okay, and that's when you add a hydrogen. So hydrogen up here kind of told you about the H3O plus, how we call it, that's a hydronium. It's a positively charged cation. We often just call it a hydrogen proton because protons are positive and it's just one positive charge. So the same concept here, this minus sign here is being replaced by this hydrogen, which is a positive charge. So that positive charge is taking the place of that minus charge. And this is called acetate. But when we add that H right there, it becomes an acid, and that 8 turns into ic. So this is acetate, CH3COO minus, and this is acetic acid, CH3COOH. And if it helps you remember, you can just say CH3Cu. So there's a little tidbit there. Going back to the polyatomic anions that have 1 minus charges. On the list, we also have the group of chlorine oxyanions. So this is the big group that you have to know. ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. So what I want you to realize is that here we have a chlorine containing oxyanion. Here we have a nitrogen containing oxyanion. And we'll get to the sulfur containing one when we get to the 2 minus charges. What I want you to realize is that here, the chlorine oxyanions, even though they have different numbers of oxygens, they still have the same 1 minus charge. Even though these have different numbers of oxygens, they still have the same 1 minus charge. The name changes based on the number of oxygens. So I'm going to tell you that nitrogen containing oxyanions only go up to NO3. So the highest one is NO3, and we call that nitrate. The one below it is nitrite. Here, this goes a little bit higher than 3 oxygens. This one is still chlorate. This is chloride. If this is chlorate and this is chloride, what would we call this? Well, we simply add per. It means 1 more oxygen. Perchlorate. Still got the 8 going on. Down here, we simply add the word hypo, or the prefix hypo. Chlorite. Ite. Alright, so on one way you can remember that is that hypo is kind of like under, right? You learn in biology about the whole water hypo stuff. So yeah, hypo. Just try to remember that. And that pretty much does it for the polyatomic anions with a 1 minus charge. So you've got bicarbonate. You don't really have to commit these to memory. I'm just going to show you something in a moment about these. you do have to memorize nitrate, nitrite, hydroxide, acetate, acetic acid. Notice that this is not a polyatomic anion. There's no charge here, but this is. And then you've got your chlorine oxyanions: perchlorate, chlorate, chlorite, and hypochlorite. Alright, so next on the list are our 2- polyatomic anions. Our polyatomic ions that have a charge of 2-. First one up is SO4 2- and SO3 2-. So we call this, so if we call this hydrogen sulfate and this hydrogen sulfite, what do you think we call this? It's simple. You just call this sulfate and sulfite. The hydrogen is not there, so you just take that out of the name. Now what I wanted to go back to was that the whole concept of hydrogens and acids. So acids contain protons. They contain hydrogens. Remember, we referred to hydrogens as protons because, I'm going to digress for just one moment. Hydrogen, it has 1 proton and 1 electron, correct? No neutrons. One way we could draw that is to say we have a proton in the middle, in the nucleus. This is an electron cloud. And we have 1 electron. Hydrogen can function as a cation or anion. Whoa, that's some serious stuff right there. If it gives this electron away, gives it to a nonmetal, it would be functioning as a cation, right? It would have given its electron away, and then it would only consist of this positive proton. So that's why we refer to hydrogen as a proton, right? And we would write it as that if it gave its electron away. Following me? So, this is sulfate and it has a 2- charge. This is sulfite and it has a 2- charge. When you add the hydrogen and you have an acid, typically, that hydrogen replaces one of those negative charges. So it's brought down from 2- to 1- because you put a proton in there, which is a positive charge. So you kind of negated that one charge, one of the 2 charges. So 2-, 1-, and it's because of the hydrogen. So that's how I wanted to connect the dots there. Same concept. Earlier up here we had HCO3-, which is bicarbonate. Or you can call it hydrogen carbonate. Most people just call it bicarbonate. It's up to you. Well, in the 2- section, we also have carbonate, which is CO3 2-. So you can call that hydrogen carbonate, and this is carbonate. And see how this went from 2- to 1- because the hydrogen is there. See how that makes sense? It's not so bad. Another polyatomic anion that has a 2- charge is O2-, and we just call that peroxide. Think back to peroxide that's in your little brown bottle, H2O2. It's that, peroxide. Notice how 2 hydrogens, there's no charge here. But with the peroxide, there are no hydrogens and there's 2-. And finally, you have a polyatomic anion that has a 3- charge. And that would be PO4 3-. We call that phosphate. That's the last one you have to memorize. You could also say that, knowing that this is that, you could infer that PO3 3- would be phosphite. But if you just know that PO4 is 3 minus and it's called phosphate, you could infer that one less oxygen would be called phosphite, but has phosphorus. It's a phosphorus-containing oxyanion, so they still have the 3 minus charges. Just different oxygens make it a different ending. Okay, so that's all for polyatomic anions and cations. Now we can move on to actually naming ionic compounds.